Alright, here we are on, it might be part 3. If I went too long on part 1, I'll split it into 2 and this will be part 3. So this is part 2 or 3. So I'm wondering what the integral is from c to the same number c of a function. So here's my function f of x. What's the area under the curve from c to c? From c to shining c. We're going to get no area. There has to be a difference between this and this in order to create an area under the curve. Like if I went c to c plus some change in x, then I would have an area. But if I just go from c to c, I create no area. It's just the line. So the integral from c to c of any function is just 0. Alright, so we will call that property number 5. Nope, where are we? No, that's property number 3. Sorry. Alright, number 4 here. I was wondering what happens when I take the integral from a to c and then the integral from c to b. I draw a picture of it, so that might help you see. So from a to c would be this area. From c to b would be this area. So what would be the, is there a way I could write this as one integral indicating all of this area? And there is, and it would be the integral from a to b of f of x dx. And that is a principle or a property of definite integrals. Alright, moving right along, let's look at property number 5. I think there are 6. Alright, this one I was wondering is what's the relationship if I exchange these limits of integration? The upper becomes the lower and the lower becomes the upper. So here I have the integral from a to b of a function, and here I have the integral from b to a of a function. So let's think about what it means in terms of a Riemann sum, and we already talked about this being equivalent to this. And I want to zero in on the change of x part, because if each of these subintervals are the same width, which they don't have to be, but if they are, it's b minus a over n for this part. And this is going to be the same as this. But what happens over here to this part? Alright, so here we're going from b to a, so this, the interval is from a to b, but on this one the interval is from b to a. So we're going to do the second minus the first over n. So what's the difference between these two numbers? Well, they are the same number, but they have opposite signs. And that will cause the same thing to happen with these integrals. These will be equal if one of them is given the opposite sign. So this principle holds. The integral from a to b of a function is negative the integral from b to a of the function. Alright, lastly, I have trouble probably sketching this one, so bear with me. Suppose I have the integral from a to b of a function, and I am wondering how I can make these equal if I add a value to the lower limit of integration and add the same value to the upper limit of integration. So I have a plus c instead of a and b plus c, but I wanted these to remain equal. What do I have to do to this function in order to keep the area under the curve the same? So this is where I had trouble drawing this one. So this is representing the area from a to b. So it's the area under the curve here. But if I add, say, a value a plus c and b plus c, then I'm looking at the area from here to here. They're not equal at all, but I want to keep them equal. Do you see? One way I can do that is to slide this whole graph down so it is C away from where it started. Then the area from here to here will be the same as it was to start with. So I'm going to slide that graph to the right, and I do that by putting a negative C in my argument. Remember, when the change hugs the x inside the argument, it creates a negative value, creates a slide to the right. So if I move the whole original graph to the right C, then I'll still have the same area under the curve as I did in the beginning. Alright, good luck with that one. So, alright, these principles, these 6 principles will be exercised in our work come Monday or soon after. Alright, talk to you later. Have a good rest of your weekend, and goodbye.